Newton figured out gravity well enough that we could fly to the moon. Ever wonder if what we know about time is just the tip of the iceberg? His big idea isn't just a theory. It's like a key that might open up a bunch of the universe's secrets, showing us things we never thought possible. So how does Brian Cox's fresh take change what we thought we knew about time, and what could that mean for how we see reality? Come along as we check out time itself, based on Brian Cox's new theory about time. In the huge place around us, there are strange things about time and gravity, the basics for how we live. Imagine a world where time gets weird, speeding up or slowing down. And what if gravity isn't what we think? That's where Einstein's theories come in. He gave us a fresh way to see the universe. Einstein's ideas from the early 1900s are the base for understanding how time acts when things move super fast. He had two big theories: special relativity and general relativity. The special theory from 1905 totally redid how we think of time and space. It says that the rules of physics are the same for everyone who isn't speeding up, no matter how they're moving. This theory gives us relativistic effects like time slowing down under some conditions. To get your head around time slowing down, think of a light clock and a fast spaceship. A light beam bounces between two mirrors. Light speed is the same for everyone, so the light seems to go further. For someone watching from outside, it seems like it takes longer for the light to travel that path. That time difference is what Einstein called time dilation. Time slows for the moving observer compared to someone standing still. Motion changes time. Knowing how things change when moving fast isn't just a thinking game. Scientists use machines like the Large Hadron Collider to speed up particles close to light speed. When things go this fast, we must consider time differently to get the right answers. Einstein's special relativity from 1905 tweaked how we see the universe, especially regarding time changes. It's not what we expect. It says physics rules are the same for everyone, no matter their motion. Usually, we think adding speed makes something go faster, but Einstein said there's a speed limit: light speed. One weird thing is that events that happen at the same time for one person might not for another moving fast. Length can also change. Moving objects look shorter in the direction they're moving. And there's the famous equation E equals mc2 E equals mc2, showing that energy and mass can swap. This helps us get how tiny particles act when zooming along and how nuclear reactions work. Special relativity isn't just a fancy thought. GPS tech uses it every day. GPS satellites send signals while moving, so time is a bit different for them. If we didn't figure in time changes, GPS would be way off. So, special relativity tells us time isn't the same for everyone based on how they're moving. It's like our normal universe view is a little wrong. According to special relativity, time isn't set. It shifts with movement. Ideas like light speed being constant and the link between energy and mass have been proven a bunch, but there's still more. Then comes Einstein's general relativity from 1915. It goes deeper into how gravity and the universe's structure are connected. It dumps the old idea that gravity just pulls things together. Instead, it says gravity happens because space and time are bent. It's the natural path of objects through this curved spacetime, not some invisible force. Think of spacetime as a huge trampoline. A heavy thing like Earth makes it dip. If you put a ball near Earth, it rolls toward the dip. That's like gravity, not a pulling force but spacetime curving. General relativity explains how planets orbit the sun, predicting how they move. It even gets why Earth's orbit is an oval, not a circle. The old idea that gravity just pulls stuff can't explain this well. Einstein's theory says space and time are like a bendable cloth twisted by heavy stuff. A solar eclipse in 1919 proved this. Sir Arthur Eddington watched how starlight bent as it passed the sun. The theory said the sun's weight would change the starlight a bit during the eclipse, and that's what they saw, proving the theory right. Just like motion can change time in special relativity, gravity messes with time too. Where gravity is strong, time slows down more than where gravity is weak. A clock near a black hole would tick slower than one far away. General relativity gives us black holes, where gravity is crazy strong. Nothing can escape, not even light. The edge of a black hole is the event horizon, and once something crosses it, it's gone. Einstein's theory has big results for the universe. First, He put a cosmological constant in his equations because he thought the universe wasn't moving. But when they found out the universe was getting bigger, he said that was a major blunder. The idea of an expanding universe from general relativity is a key part of the Big Bang theory, describing how the universe started. Another important idea is gravitational waves. These are waves in spacetime made by heavy things moving fast. In 2015, scientists at LIGO found gravitational waves, proving another piece of Einstein's theory. Over time, scientists have tested relativity a bunch, and it keeps passing, whether watching starlight bend or seeing gravitational waves. General relativity is still solid. Saying gravity is false is tough, especially since we feel it every day. In physics, folks often talk about different ideas. Some, like Brian Cox, question the usual views. One idea is modified Newtonian dynamics, which says gravity acts differently at slow speeds inside galaxies. Instead of needing invisible dark matter, Mond says gravity is stronger at low speeds. The gravity talks also bring up dark matter and dark energy to explain some things in space. Some say those aren't needed and other theories work. Some scientists against Einstein's gravity look at new options, like unknown particles or forces that could tweak gravity. New ideas are tried hard to see if they hold up. Einstein's idea of time in four-dimensional space, where time travel is kept by light speed, has sparked new ideas. Concepts like shortcuts and wormholes were looked at by Stephen Hawking, who thought time travel was unlikely. Ongoing tests see if these new theories can explain gravity well. While many things have been talked about, nothing has beaten relativity yet. Questioning gravity and the norm is key to science. It lets us learn more and get the universe better. Gravity theories keep changing, but relativity is still the best. Despite problems and different ideas, it does well in tests and explains planetary motion and light bending. So, general relativity is still good because it's simple and covers a lot. Like we said, special relativity says time changes with motion. So, how does that affect space travel? Space travel is tough since space is big. Einstein said light speed is the ultimate limit, and that makes star travel hard, even with tech. Think of the twin paradox. One twin stays on Earth while the other goes zooming to a star. When the space twin returns, they've aged less than the Earth twin. They've gone into the future. Time is important for space travelers because longer trips mean greater slowing of time. If astronauts visited nearby stars, time would slow a lot, and they might age slower than Earthlings. Sounds like sci-fi, but it's relativity in action. Imagine a crew going to a star system nearby. The trip could take years, even going fast. How does Brian Cox's time idea mess with what we thought we knew? What could this mean for how we see reality? Let's check out Brian Cox's new time theory and the huge universe around us. There are secrets waiting to be found, like weird stuff about time and gravity, which are super important. Imagine a world where time is strange, speeding up or slowing down. And what if gravity isn't what it seems? That's where Einstein's relativity comes in, changing how we see time and gravity. Einstein gave us a new way to look at the universe with his relativity theories. His work helps us get how time acts in different places, mostly when moving super fast. It all started around 1900 when Einstein shared two big theories: special and general relativity. The special relativity theory from 1905 changed how we see time and space. Simply put, physics works the same for everyone who isn't speeding up, no matter how they're moving. This brings up cool stuff like time slowing down under special situations. A cool way to get time slowing down is to think about a light clock. Imagine being in a super-fast spaceship. Inside, there's a light beam bouncing between two mirrors. The speed of light is the same for everyone, so the light seems to travel a longer path. The time it takes should be the same inside and outside the spaceship, but since the path looks longer for the outside person, it seems like it takes longer for the light to finish its trip. This difference is what Einstein called time slowing down. Time slows down for the person moving compared to the one standing still. Understanding how things change when they move fast isn't just a theory. Scientists use huge machines like the Large Hadron Collider to make tiny bits move super fast, nearly the speed of light. When things move this fast, we have to think about time differently to get things right. Einstein's special relativity changed how we see the universe, especially when it comes to time changes. This messes with our normal thinking. The rules of physics are the same for everyone, no matter how they're moving. Unlike our everyday thinking, where adding speed just makes things go faster, Einstein said there's a top speed, the speed of light. Another cool result is length contraction. Moving things look shorter in the direction they're moving when viewed from a still spot. Then there's the famous equation E equals mc2 E equals mc2, showing that energy and mass can switch into each other. This is key for knowing how tiny bits act when moving fast and for things like nuclear reactions. Special relativity isn't just a fancy idea. We use it every day. GPS stuff depends on it because GPS satellites are moving. Time acts a bit different for them. If we didn't think about time slowing down, GPS would be way off. Special relativity shows us that time isn't the same for everyone, and it all depends on how things are moving. So, time isn't set in stone. It changes with movement. Ideas like the speed of light staying the same and the link between energy and mass have been proven a bunch, but there's still more. Einstein's general relativity theory from 1915 goes deeper into how gravity and the universe's shape are related. It says gravity isn't just a force pulling things together. It happens because space and time are curved. Einstein's theories have reshaped the way we understand time and space, giving us the tools to explore and predict complex cosmic phenomena. But as scientists continue to push the boundaries of our understanding, new theories and ideas are being explored to enhance, or even replace, some aspects of relativity. One key area where these new ideas come into play is the concept of quantum mechanics. While relativity works well on large scales, such as explaining the motion of planets or the bending of light by gravity, it struggles to explain phenomena on the quantum level, like the behavior of particles at the smallest scales. Quantum mechanics, which governs the behavior of subatomic particles, operates on a different set of rules than those laid out by Einstein. For example, particles can exist in multiple states at once and their behaviors can only be described probabilistically. Relativity, in contrast, deals with deterministic rules that predict exact outcomes. This discrepancy between the quantum world and the relativistic world presents a challenge for physicists seeking to unify these two models into a single theory of everything. One promising approach to bridge this gap is string theory. String theory proposes that the fundamental particles of the universe are not point-like objects, but rather tiny, vibrating strings. These strings can exist in multiple dimensions, beyond the familiar three-dimensional space we experience. String theory suggests that the universe may have more than the 4 dimensions we observe, 3 spatial dimensions and time, possibly as many as 10 or 11. These extra dimensions are thought to be compactified, meaning they are incredibly small and not observable at our scale. By incorporating extra dimensions, string theory could potentially reconcile the differences between relativity and quantum mechanics. Another idea that's gaining attention is the concept of quantum gravity. Quantum gravity seeks to merge the principles of general relativity with the laws of quantum mechanics. In classical relativity, gravity is seen as the curvature of spacetime caused by mass and energy. However, quantum gravity proposes that this curvature might be caused by quantum fluctuations, which are small, random changes in the energy of a system. These fluctuations could potentially be observed in the fabric of spacetime itself, revealing a more granular structure at the smallest scales. One potential outcome of this research could be the development of a theory of quantum spacetime. This could offer insights into the true nature of time and space, particularly under extreme conditions, such as near black holes or during the earliest moments of the Big Bang. The study of quantum spacetime might even reveal that spacetime itself is not a smooth, continuous entity, but rather a dynamic, granular structure that behaves differently on the quantum scale. The concept of time itself is also being re-examined in light of modern advancements in physics. While Einstein's theory of relativity introduced the idea that time is not absolute, researchers like Brian Cox are suggesting that there may be even deeper layers to the nature of time. For instance, what if time doesn't flow uniformly in all places, or what if it isn't a linear progression as we experience it? Some ideas propose that time could be cyclical, or even that the flow of time might be an illusion, a product of the way our brains perceive the universe. The exploration of these ideas could have profound implications not just for physics, but for our understanding of consciousness, the arrow of time, and the nature of reality itself. In fact, Some physicists are investigating the possibility that time may be emergent rather than fundamental. In this view, time arises as a result of more fundamental processes, such as the interactions of particles at the quantum level. If time is emergent, it might not be a constant backdrop against which events unfold, but rather something that arises from the underlying dynamics of the universe. This would challenge the classical view of time as a linear progression and could open up entirely new ways of understanding the cosmos. Another intriguing aspect of modern physics involves the idea of parallel universes or the multiverse. According to some interpretations of quantum mechanics, every possible outcome of an event could occur in a separate parallel universe. This idea was proposed by Hugh Everett in the 1950s and has gained traction in recent years. If true, this could mean that there are an infinite number of universes, each with its own version of time. Some universes could be very similar to ours, while others might be radically different. The study of parallel universes could lead to new insights into the nature of time, as well as the fundamental structure of reality. Even concepts that were once purely speculative, like wormholes and time travel, are being taken more seriously by physicists. While Einstein's theory of relativity allows for the mathematical possibility of wormholes, shortcuts through spacetime that could, in theory, connect distant parts of the universe, there's still much we don't know about how they could actually exist. Some researchers believe that wormholes could allow for faster-than-light travel, potentially opening the door to interstellar exploration and time travel. However, the practical challenges of creating or stabilizing a wormhole are immense, and many questions remain unanswered. One of the big unknowns when it comes to understanding time and gravity is the role of dark matter and dark energy. These mysterious substances are thought to make up most of the universe, but they remain largely invisible to us, detected only through their gravitational effects. Understanding how dark matter and dark energy interact with spacetime could be key to unlocking the deeper mysteries of gravity and time. Some scientists believe that dark matter may even interact with gravity in ways that we do not yet fully understand, leading to new insights into the fundamental nature of spacetime. In conclusion, while Einstein's theories of relativity have provided us with a powerful framework for understanding the universe, there is still much to discover. As we explore new ideas in quantum mechanics, string theory, quantum gravity, and the nature of time itself, we are beginning to realize that the universe is far stranger and more complex than we ever imagined. Whether through new theories or discoveries, the future of physics holds exciting possibilities that could redefine our understanding of time, space, and reality itself. The journey is far from over, and the deeper we look, the more we might find.